This is a very advanced technique that we are going to learn, and we will demonstrate this also using a work sample to you. This technique can provide you the all the information of the material just like pulse. You know very well, human being is having a pulse that can be examined by a doctor at this location. So if the doctor is expert, he can check the pulse rate of a patient, and by analyzing that pulse within a fraction of minute, the doctor is able to inform the patient that you are having hypertension, you are having some fever, you are having this kind of infection, and this is the remedial action in terms of medicine. This technique I will show you. Okay, so this is the instrument. So, I hope this instrument is visible to you since this is the lab section. So we'll study some instruments. And this instrument is having name Barkhausen noise analyzer. So this is the analyzer, and this is the display device, that is the laptop. Okay. So first we have to switch on the analyzer. So this is the switch on button. I will have to on this and then power on. So this red color is indicating that power has been on in this analyzer. It is ready to use. How this analyzer will display the information that we will see in this laptop. So this laptop is having an icon that is Mag Star. The name of this analyzer is Mag Star. So we are using to we are going to use this instrument by using the control panel. So this is the control panel. And this is the display device. This display device is displaying a message that the display has been connected to the Magstar successfully. So this is a message that indicates we have connected successfully the display unit with the analyzer. Now, this Technophore is a company which has provided or which has manufactured this instrument in collaboration with NML Jamshedpur, that is National Meteorological Lab. And this instrument provides two options: PH loop, that is Barkhausen loop, and second is Barkhausen noise signal. So we are having these two options. How we are going to use this? Just a minute. Okay. So this is the Barkhausen noise signal that we will discuss later on. And this is the hysteresis loop analysis. So how we will analyze the material? Suppose I am considering this is the workpiece material. This workpiece material inspection I am going to carry out with the help of this instrument. So this is the probe. This is the probe. By using this probe, I can analyze the health of the material. How I can. So you can see the yoke closely. This yoke is having name magnetizing yoke, and this is having two legs. First leg is there, second leg is there. So this is the leg of magnetizing yoke, and this one, the circular part, this is sensor. So with the help of these magnetizing leg, I will apply the magnetic field and this sensor will detect the signal that is coming out from the material. How it will act? I am keeping this over the material like this, okay, and then I am going to start the test. So the display will indicate the health. So we are able to get a hysteresis loop. You can see this is the hysteresis loop, and this hysteresis loop is having several parameters. These are the parameters: permeability, coercivity, remanence, area of loop. These are the parameters. These we will discuss later on. Again, once again, we are getting the hysteresis loop. So now you can see formation of a very good hysteresis loop. So this is the hysteresis loop that we have obtained. Again, we can have a look. So you can see on the display that formation of hysteresis loop is going on. Okay. So this is the hysteresis loop that we obtained from this material, workpiece material, and its characterizing parameters are there. Permeability is there. You can see permeability is there. You can see coercivity, remanence, core loss, and flux density. How these parameters are indicating the health that we will see in our presentation. The another option of this instrument is Barkhausen noise parameter. Again, this yoke will apply the magnetic field. How we can assess the health? So if I start the test, then this signal that you are able to see is Barkhausen noise signal. How this signal and hysteresis loop is beneficial in surface characterization that we will see in our PowerPoint presentation. So this is the first demonstration. I will explain you the principle of this technique. Then again we will repeat this lab session after completion of presentation. To explain the principle of this technique, I have prepared a presentation. That presentation I will share with you. I will explain you the fundamental of this technique, that is Barkhausen technique, very advanced technique nowadays, and how it is applicable in manufacturing, that we will see. I hope the first slide is visible to you, all of you. It is a smart characterization of material. You are able to see the generation of Barkhausen noise signal at the left hand side, and at the right hand side it is hysteresis loop generation, that is magnetic hysteresis loop. Is it visible to you, all of you? So this slide is indicating formation of a hysteresis loop and generation of Barkhausen noise signal. What is advanced material characterization or smart material characterization, and how it is applicable in manufacturing engineering, that we will see. First thing, what is material characterization, why it is required in manufacturing engineering, and what is the meaning of smart material characterization or advanced material characterization. So first, what is the meaning of material characterization? Material can be characterized by its microstructural state, micro hardness variation, its surface roughness value, what are the phases present in material, as well as, very important, the nature of residual stress. Intentionally, I have kept this nature of residual stress in red color font because among all these five elements, the nature of residual stress is very, very important. So, we have to assess the residual stress critically because it is nowadays very much important. Why material characterization or smart characterization is required in manufacturing engineering? Quality is a term that is very popularly used in case of manufacturing. The quality of a manufactured product is assessed by the surface integrity of the manufactured product. This surface integrity of component or manufactured component is integration of, or it is summation of, microstructure state, micro hardness variation, surface roughness, phase analysis, and nature of residual stress. So, by comparing the definition of surface integrity and material characterization, we came to know that material characterization is nothing but assessment of surface integrity. Material characterization as well as the surface integrity of product both are assessed by microstructural state, micro hardness variation, surface roughness, phase analysis, and nature of residual stress. That is why material characterization is essential in manufacturing industries. What is the requirement of advanced or smart material characterization? If we look into the conventional techniques of material characterization, then we are having five most popular techniques. Those are optical microscope, micro hardness tester, roughness tester, X-ray diffraction technique. If we consider the optical microscope that is used for assessment of microstructural state, then the cost of procurement of this optical microscope is 15 to 20 lakh rupees, and it require 1 to 2 hour time to analyze the microstructure of component. We require polishing over the emery paper, we require diamond polishing, we require etching, then we require image analysis in optical microscope. So this combined time is around 1 to 2 hour. In case of assessment of micro hardness testing, micro hardness tester is there. This micro hardness tester is also procured in the same cost range in which we can procure the optical microscope, that is 15 to 20 lakh rupees. The time to assess the micro hardness of the component is approximately half an hour to 1 hour. Then to check the surface roughness or to assess the surface finish, roughness tester is there. This portable instrument or very small instrument is available within 3 to 10 lakh range, and it can provide the surface finish within 10 minutes. Now, very important machine or technique is X-ray diffraction technique or XRD technique. This technique is required for assessment of phase as well as nature of residual stress. The cost of this technique, I repeat, the cost of procurement of basic instrument of this technique is 1 crore rupees. That is quite huge amount, and it requires also more than 1 hour time to analyze the residual stress. So these are the conventional techniques. If we sum up the cost of procurement of all these techniques, then it is around 1.5 crore rupees. So we have to purchase these techniques by investing 1.5 crore rupees, as well as the time will be around 3 hours if we have to assess the health of the component or the material by using this conventional technique. This 1.5 crore rupees is huge amount, but more importantly is the time. The time is around more than 2 hours to assess the health of a manufactured component. This is not permissible in modern manufacturing because we are producing the component in large quantity in mass. So in mass production, if we are investing more than 2 hours to assess the quality or the health of a manufactured component, then this is against the economy. This is not preferable. So what is the answer that we are having? The answer is Barkhausen noise technique. The demonstration of this technique just we have seen. This technique is used for microstructure state analysis, to assess the micro hardness variation, for analysis of phase and nature of residual stress. The residual stress is very important. It is defined as the amount of stress that is remained in the component, manufactured component, under unloaded condition. So when you remove all the load, and if the workpiece material or the manufactured component is having any amount of stress, that is the residual stress. And this residual stress, it can be compressive in nature or it can be tensile in nature. So the nature of residual stress is very important in manufactured component that we will see in coming slides. The most important is the time of analysis. The time of analysis we have seen in case of conventional technique, it is more than 2 hours, but if we are going for this smart characterization technique, then the time taken is 5 minutes only. I repeat, time taken is only 5 minutes, and the instrument that you have seen, it is Megastar instrument. We have procured it from Techno4 Pune, that has produced this in collaboration with uh, National Meteorological Lab Jamshedpur. So this scientific instrument is having cost around 15 lakh rupees. So in comparison to 1.5 crore, you are investing only 15 lakh rupees, as well as the time that you have reduced in analysis. It is from 2 hour to 5 minutes. So that is the main advantage of this advanced material characterization technique, having name Barkhausen noise technique. For assessment of surface integrity, we can use our naked eye. By using the visual inspection, we can assess the surface roughness or any deflection or deformation over the top surface of the workpiece material. In case of micro hardness inspection, we have to use a micro hardness tester. That micro hardness tester provides a indentation over the workpiece material. This indentation size or diameter will provide us the information regarding the micro hardness. We are having very common instrument, that is metallography inspection optical microscope. So this optical microscope will provide us the information about the microstructure, or that is used in case of metallographic studies. Roughness tester is another instrument that is required for assessment of surface finish. The most important element is residual stress. I have repeated this is several times. So this most important element, that is residual stress, it is assessed by a technique, that is X-ray diffraction technique. So in case of manufacturing process, we know that raw material is converted into useful object, and this conversion can be possible by four classified methods. These four classified methods or popular methods are forming method, so that is the plastic deformation category; material addition, that is the change in shape and dimension of the component by using addition of material like welding, brazing, soldering, and even in electroplating. Melting and solidification is another classification of manufacturing process. In case of casting process, you have seen this shape conversion or manufacturing of product by melting and solidification phenomenon. The fourth one is very important. Fourth one classification is metal removal classification. Why I have written it in bold? Because if we divide manufacturing process in four categories like forming, metal addition, melting and solidification, and metal removal category, then major portion of these, I repeat, major portion of these, it means around 62% is covered by metal removal category. That is why I have kept it into bold font. So this is the participation index. It is indicating that mainly manufacturing process are covered by metal removal category like drilling, machining, shaping, grinding. In all these cases, we are converting the shape of raw material or supplied material by removing the material from desired location using a machine tool and cutting tool. In case of metal removal category, we are having very common process: turning, shaping, planing, drilling, milling, broaching, gear manufacturing, thread cutting, and last one is grinding. So, to explain the application of Barkhausen noise technique or its applicability in manufacturing, I have used a process that is very common, and we have studied this process in our previous lecture session from 11:30 to 12:30, that was grinding. So to explain this technique in very easy way, again I have opted or I have selected the same process, that is grinding. So in case of grinding, we know that abrasive grit act as a cutting tool, and these abrasive grits are having large negative rake angle. Because of that large negative rake angle, large amount of cutting forces are generated, and which generate enormous amount of heat in form of spark, or we can say chingari. So these chingari or sparks are only in grinding process. So this is the inherent characteristics of grinding. We cannot change this negative rake angle, as well as we cannot control the geometry of workpiece. Sorry, we cannot control the geometry of abrasive grid. It is irregular in shape. So if we consider the characteristics of grinding, we know that large amount of heat is generated because of large negative rake angle, because of ploughing action of abrasive grit over the workpiece, as well as because of some amount of rubbing of abrasive grit over the workpiece surface. Large amount of heat is always generated in this last machining process or last tooling process. This large amount of heat that is generated in grinding process, it is transferred. We know that heat is having capability transfer itself in atmosphere or in surrounding media by three modes. The first mode is the radiation, second mode is the conduction, and third mode is the convection. So in case of machining or in case of grinding, this large amount of heat is conducted into the abrasive grit, into the grinding chips, and into the workpiece. And some amount of heat is transferred to the air or coolant through convection or radiation. By looking this figure critically, if we look into the size of arrow, the size of arrow is indicating the amount of heat transfer. According to experimental data, these size of arrow has been decided. So this size of arrow is indicating that the grinding heat or the machining heat, large amount of this heat is transferred into the workpiece. Okay, and very small amount of heat is carried out by the coolant or air. Very small amount of heat is taken away by chip, and also very small amount of heat is also taken away by abrasive grit. In this case, in conventional grinding, we are using abrasive grit which is made of alumina or silicon carbide. The thermal conductivity of heat, these abrasive grit is very important. Alumina and silicon carbide thermal conductivity is very small. It is around 40 watt per meter Kelvin, or it is 45 watt per meter Kelvin. So you can imagine that this amount of thermal conductivity is less, or I can say poor thermal conductivity. That is why less amount of heat is being transferred into the abrasive grid. So what is the solution? In case of our previous lecture, we have seen that if we use super abrasive grade like CBN cubic boron nitride or diamond abrasive grade, then these abrasive grade, diamond is hardest available material, CBN cubic boron nitride is second hardest available material on the earth. But the biggest advantage of these super abrasive grit is their very high thermal conductivity. The thermal conductivity of diamond and CBN is around 250 watt per meter Kelvin. So if we are using this thermal conductivity, then heat, large amount of heat will also transfer into the abrasive grid. Now, again, a significant amount of heat will transfer into the workpiece. If this significant amount of heat is transferring into the workpiece, what will happen? This figure is indicating a grinding operation, and the rectangular block is having some information in terms of microstructure, in terms of crack, hardness variation, and residual stress. So in previous slide, so in previous slide, गणेश जी मैं ऑनलाइन मीटिंग में हूँ, मैं आपको बाद में फोन करता हूँ अभी. क्या कर साइन आज मैं एक्चुअली 1 बजे तक 6:30 बजे तक रहूंगा इस मीटिंग में. ऑनलाइन चल रही है, 6:30 बजे बाद आ जाऊँ? है? अच्छा। हाँ हाँ, तो कब आऊँ? ठीक ठीक ठीक। ठीक 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 ठीक। So in previous slide we have seen that large amount of heat is transferred into the workpiece. If this large amount of heat will transfer into the workpiece, then what will happen? This large amount of heat will definitely going to change the microstructure of the workpiece material. So you can see that in microstructure we are having very dark black layer, then followed by white layer, then followed by brown layer or dull black layer. So this is indicating variation in microstructure. Generally, we require very uniform workpiece when we are going to manufacture a component. So this non-uniformity in microstructure is not desirable. And unfortunately, this non-uniformity in microstructure is coming in last machining operation or last tooling operation. This heat will also alter the micro hardness. The micro hardness of the top surface will be more in comparison to the micro hardness at subsurface level or at the center. That is again not desirable. We are applying the heat. This heat is in enormous amount as indicated by spark, as well as we are also applying the coolant. So we are performing a quenching operation. We are applying large amount of heat. We are cooling the workpiece simultaneously by coolant. So this will introduce surface crack as well as subsurface crack. That is again not desirable during the quality inspection. Last but not least, that is very important. It is the induction of tensile residual stress. So this tensile residual stress will be detrimental for manufactured component that is coming from last machining operation. So as the name is indicating, this residual stress that is induced by heat, it is tensile in nature like this. It is tensile in nature. So all along we have seen that elevated temperature in grinding zone will introduce thermal damage in form of grinding burn marks, metallurgical changes, micro hardness variation, formation of crack at surface and subsurface, as well as induction of tensile residual stress. And this has been proven by scientific community. Various scientists who are working in the area of grinding, they have clearly informed that tensile residual stress is main problem in grinding. Marshall and Shaw are well-known scientists in the area of machining or in the area of manufacturing. In 1952, they declared in an article in ASME that this is main problem in grinding and it should be avoided, or we have to take some remedial action, or we have to measure the tensile residual stress in the component. Another group of scientists, Brinksmeyer et al. He is also very popular name in area of manufacturing. This group has also declared in an article in NLCIRP in 1982 that tensile residual stress detrimentally reduces the static strength as well as the fatigue life of product. So these critical analysis by well-known scientists are indicating the need of advanced surface characterization or smart surface characterization for quality improvement in manufacturing. Now we came to know that in case of grinding, heat is generated and this heat is problematic because it is inducing tensile residual stress. This tensile residual stress is the main cause of poor quality of manufactured component. So, in nutshell, we came to know that assessment of surface integrity is very important in manufacturing, because by assessing the surface integrity, we will come to know about the quality of manufactured component. And in manufacturing, the quality or the surface finish is mainly governed by a process. That process is having name grinding. Unfortunately, in grinding, heat is generated, and this heat is not good for good surface integrity or good quality of component. So, the main cause of poor surface integrity or poor quality of manufactured component upon grinding is induction of tensile residual stress. This tensile residual stress is detrimental to the service life as well as fatigue life of the component. Now the big question is, why tensile residual stress is detrimental? If we look into this rectangular block and suppose this rectangular block is a manufactured component from a supplied material or raw material, then all of us know very well that nowadays we are not able to produce a perfect workpiece material. We are not able to produce 100% accurate workpiece material or component. Why? Because the component or the work material that we are producing, it is always having defects in form of cracks or porosity, as well as it is also having voids. So it is having cracks, porosity, voids, secondary particle inclusion, carbide inclusion. So because of these, we are not able to produce 100% accurate manufactured workpiece material or component. Now, if the component or manufactured component or component after grinding is having all these effects like crack, void, porosity, as well as if it is having tensile residual stress, then the nature of tensile residual stress is like this. It is trying to elongate the workpiece in this fashion. So if this is the direction of stress, it is elongating each and everything. Okay, it is going to elongate each and everything inside the workpiece material. So without differentiating or without biasing, it will also elongate the size of crack, size of void, as well as size of porosity. So the defect size or the imperfection size will increase with induction of tensile residual stress. That is why the tensile residual stress is not required. It detrimentally reduces the static strength and the fatigue life of the product or manufactured component. Hence, we have to have assess the residual stress. So, we came to know that it is very much essential to assess the residual stress for characterization of material or for assessment of quality of manufactured product. How we can assess the residual stress? We are having various techniques. These techniques are optical inspection, mechanical technique like hole drilling methods. We are having strain gauge based method. We are also having neutron dissection technique that is very costly, and we are also having a very popular and well established technique, that is X-ray diffraction technique or XRD technique for assessment of residual stress. So this is the actual figure of X-ray diffraction technique. You can see that it is having a goniometer. That goniometer can rotate along the horizontal axis for measurement or for scanning of the workpiece, for measurement or assessment of residual stress. This basic instrument that is manufactured by Philips or Pan Analytical Company or Bruker Company, this basic instrument, I repeat, this is the basic instrument. It is not the advanced version of this technique, not modified version of this technique. This basic instrument cost around 1 crore rupees. Okay, so this technique, that is very popular technique or well established technique used for measurement of residual stress, is a standard practice. It provides absolute value of residual stress in terms of megapascal. And the major advantage is we can get very repetitive measurement by this technique. So this is the schematic principle of X-ray diffraction machine. How we can assess the residual stress by using this technique. We know that material is, each and every material has been made by crystallographic plane. So in this slide you are getting the information regarding the planes. These planes are having atoms indicated by black color solid circles. So black color solid circles are indicating the atomic arrangement in a plane. So the plane is having interplanar distance. I repeat, each plane is separated by another plane, and this distance between these two planes is having name interplanar distance, that is indicated by DO. Okay, so what will happen if I apply tensile residual stress over a workpiece material? Then definitely this elongation will reduce the interplanar distance between two crystallography plane. So you can see in figure A, the planes are having DO distance. In figure B, when we apply tensile residual stress, the distance between crystallography plane has decreased. It is small d. X-ray diffraction technique uses X-ray source and X-ray detector. By using this X-ray source and X-ray detector, we can easily measure this interplanar distance. Okay, and the amount of reduction or increase in interplanar distance is directly proportional to the amount of tensile residual stress or compressive residual stress. If we apply tensile residual stress, distance will reduce, but if we apply compressive residual stress, distance will increase. So by measuring this interplanar distance before and after, and using this very famous Bragg's law, n lambda is equal to 2d sine theta, and using this equation, in this equation d is indicating the distance, E is Young modulus of elasticity, mu is the Poisson ratio. By using this mathematical expression, we can assess the residual stress in megapascal accurately. So this is the principle of measurement of residual stress by X-ray diffraction technique. So what is the limitation, or what are the disadvantage of this X-ray diffraction technique? From all direct technique for residual stress analysis, it has been already declared that XRD or X-ray diffraction technique is most reliable technique, but the limitation is measurement time is higher. It is more than 1 hour. I repeat, it is more than 1 hour. So in mass production, when you are going to produce 50,000 component or 60,000 component per day, and on sample basis using the sampling plan, if you are taking a sampling of 50 components, then it will require complete day. Okay, it will require more than 2 days for analysis. So this is the biggest advantage or limitation. Other limitations of this technique is, this technique is based on laboratory based technique. You have to establish a lab, you have to establish a room, in which this technique along with its other component like chiller unit, like power source, you have to establish. This technique is work conjunctive. What is the meaning of work conjunctive? You have to cut a sample of 35 milligram. That 35 milligram sample you have to put or you have to keep on the holder of goniometer. So this technique is work conjunctive, or limited sample size can be assessed, and the measurement depth is very less. It is 10 micron, because the depth of penetration of X-ray inside the material is 10 micron. So you can assess the depth or you can assess the health of component up to 10 micron thickness. This technique, I repeat, this technique is expensive because starting or initial cost is 1 crore rupees. Since we have to cut the sample from the component, so this technique comes under the category of not non-destructive technique. The solution or the smart characterization technique is Barkhausen noise technique. This is the signal, that is the Barkhausen noise signal. This signal you have also seen in the display that we have just demonstrated using the Barkhausen noise analyzer. So this signal is Barkhausen noise signal, and the technique or analyzer name is Barkhausen noise analyzer. What are the advantage of Barkhausen noise technique over X-ray diffraction technique or over XRD? First, it is faster measurement. I told you earlier that in case of XRD, we have to devote more than 1 hour. But in case of this technique, you have also seen during the demonstration, within fraction of minute, we were able to get the Barkhausen noise signal as well as hysteresis loop. The depth of measurement is also quite high in case of Barkhausen noise, because we are having a parameter, that is magnetizing frequency. This magnetizing frequency enables us to increase the depth of magnetic field into the material, that we will see in coming slide. The equipment, you have also seen the equipment that I have shown you. It is a tabletop equipment. The weight of the equipment that I have shown you is around 7 to 8 kg. So the equipment is portable. Suppose I have to inspect railway bridge or railway track. I cannot take the X-ray diffraction technique, but Barkhausen noise analyzer is portable instrument. I can take this instrument to a railway track or railway bridges or any other, for any other field application. I can take this instrument in a briefcase. Any complex shape it can analyze. Okay, whether it is the wheel of train, wheel of bogie, U shape of bogie, or it can also analyze the gear tooth profile very easily. So this is the most important advantage of this technique. It can analyze any complex shape within fraction of minute. Since we are not going to cut the work component or the manufactured component, so this technique comes under totally non-destructive technique. So what is the principle of this technique? We have seen the principle of X-ray diffraction technique. Now we are going to study the principle of this technique, Barkhausen noise technique. This technique is based on magnetism. You have also seen when I used the yoke, that yoke was having a magnetizing yoke. So this technique uses magnetic field. So before going into the deep fundamental of this, first we will briefly cover what is magnetism. You have seen the permanent magnet in your day-to-day life or in your childhood days. Rectangular bar magnet you have seen. You have also seen U-shape or horseshoe magnet and needle type magnet. So these magnets you have seen. What is the characteristics of these magnets? These magnets attract the alpine, or these magnets attract the iron piece towards them. Okay. So this is the basic characteristics of magnet or permanent magnet. It attracts the iron piece or ferrous material towards itself. Suppose this is a permanent magnet of rectangular shape, and I am having a alpine here. Okay, I am having a alpine here. It will be attracted towards this magnet if it is within the domain of magnetic field. I repeat, if this alpine is within the domain of magnetic field, suppose this is the alpine, this is the alpine, it will be attracted when it will be in domain of magnetic field. But suppose if alpine is there, if it alpine is there, it will not going to be attracted. So I can say that magnetic field is having a domain, or it is having a boundary, it is having a exterior. In this exterior or in this domain boundary, it can attract the iron piece. Okay, so these magnets are having a domain or boundary. In this boundary, we can feel the effect of magnetic field. So this boundary is very important characteristic. It is having a domain wall or domain boundary. Suppose this is the location of a iron piece. This iron piece is not going to be attracted if it is far away from the domain of magnetic field, or it is far away from the boundary of magnetic field. But what will happen if this iron piece is inside the domain of magnetic field? Then definitely it will be attracted towards iron like this. Okay, in case of permanent magnet, they are having magnetic field strength, but this magnetic field strength is constant. I repeat, the magnetic field strength of permanent magnet is constant. We cannot vary this strength, but we are having alternative to change the strength of magnetic field if we are replacing the permanent magnet by electromagnet. So in case of electromagnet, we are having flow of current, and this flow of current will generate magnetic field. We can change the strength of magnetic field by increasing or decreasing the magnitude of current and number of coils also. This is the very basic common fundamental of electromagnet that we have gone through in physics of 12th class or 11th class. So we can generate magnetic field always by flow of current that you can see here, and this arrow is indicating the direction of current, and blue color circle is indicating the generation of magnetic field that is associated with the flow of current. Interestingly, you can see that the magnetic field is always perpendicular to the electric field, or magnetic field is always generated perpendicular to the direction of electric current. So this schematic is indicating that the magnetic field is generated by flow of current. So whenever there is any flow of current, we will be able to feel the magnetic field. The fundamental is flow of current will always generate magnetic field. Now, here if we define the current, then we can define the current. It is nothing but it is the flow of free electron. It is the flow of free electron that will generate the magnetic field. So now we can modify the definition. We can also say flow or motion of free electron will generate the magnetic field like this figure. Now we can also see here that magnetism and electricity is well connected with each other. Whenever there is flow of current or flow of electricity, or when there is flow of free electron, we will definitely get generation of magnetic field. Okay, if we apply or if we use this fundamental over any flow of electron, then we can directly say, we can directly relate, flow of free electron will always generate magnetic field. If we apply this principle to the material, then material is composed of electrons, it is composed of neutron and proton, but we have this information that electrons are moving element. Electrons are moving element. So according to fundamental, any flow of electron will generate the magnetic field. Inside the material, electrons are moving. Will they generate the magnetic field, or can we see this magnetic field? Yes, as per fundamental, this motion of free electron will generate the magnetic field. And nowadays, we are able to see magnetic field like microstructure of material. We can use optical microscope to see the microstructure. In microstructure, we can see the grain boundary, we can see phase like pearlite or like ferrite, and we are having instrument. The name of that instrument is magnetoforce microscope. By using the magnetoforce microscope, we can see the magnetic field. So this is the actual image of magnetic field inside the material. You can see black color boundary is the domain wall or external boundary of magnetic field. Various domains of magnetic field you can see inside the material. So these black color boundaries are indicating the orientations of magnetic field inside the material. Clearly or interestingly, you can see that these domains are not orientated in a regular pattern. They are orientated or positioned themselves in a random fashion or random orientation. Why they are having this random orientation? Because according to stability criteria, everyone wants its stability, or we want to remain stable. You also want to remain stable, I also want to remain stable. So when these magnetic domains are having magnetic field, they are having magnetic energy. So because of this energy, they are having instability. So by randomly orienting themselves inside the material, they are neutralizing, I repeat, they are neutralizing the effect of magnetic field of each other, or they are neutralizing the effect of magnetic field of their neighbor. पड़ोसी ने पड़ोसी को हेल्प किया और मैग्नेटिक फील्ड को न्यूट्रलाइज कर दिया. That is why by this random orientation they are acquiring stability criteria. So this random orientation is indicating stability condition. This is another picture by magnetoforce microscopy. You can also see that magnetic domains are having random orientation. So these domains are having random orientation, and this schematic is indicating the random orientation of magnetic domain. You can see the direction of arrow. This direction of arrow is indicating the random orientation or random position of magnetic domain. They are now in stable condition. But what will happen if I provide external effect or external force or energy? You can see, suppose this pencil is having stability in this orientation and position. If I apply external force like this, or if I apply energy over the pencil like this, it will definitely change its position. So whenever I will give any motivation force or any driving force over these magnetic domain, by using that energy, again they will come into unstable state. Okay, again they will come into unstable state. So I am providing external magnetic field. I want to change their random orientation. So I am applying external magnetic field over this component. So this is the figure that is indicating the application of magnetic field over this component. So when we apply this external magnetic field, magnetic domain will receive the magnetization energy. They will receive the driving force or motivating force. By receiving this magnetic field strength or energizing force, again they will become unstable. So they will again try to acquire the stability condition. In this case, there is only one position in which they can acquire the stability condition, that is align themselves in the direction of magnetic field. So if these domain, after receiving the magnetization energy, if they align themselves in the direction of magnetic field, then they will be able to again acquire the stability. So this is the principle, or this is the basic behind the generation of Barkhausen noise signal. Why this motion will occur? Because suppose this is the orientation of magnetic field. When I apply magnetic field, it will reorient itself like this, like this, like this, and it will reorient in this fashion. So we came to know that when we apply magnetic field, when we apply external magnetic field, magnetic domain will move inside the material. I repeat, it is the motion of magnetic field inside the material. Now, I want to recall one very popular experiment of physics that we have conducted in our 12th class or in our 11th class. Suppose this is ammeter, a very popular instrument for measurement of current. Suppose in my hand I am having ammeter, and in my another hand I am having a permanent magnet. Okay, remember one thing, there is no wire connection. I repeat, there is no wire connection between this permanent magnet and this ammeter. If I move this permanent magnet towards the ammeter, the needle of this permanent ammeter will deflect like this, either towards you or towards me. And if I take away the permanent magnet, again the needle will move in this direction or in this direction. What is the indication? What is the message that we are getting? Any motion of permanent magnet, I repeat, any motion of permanent magnet induce the electric pulse that has reflected the needle of ammeter. So the motion of magnetic field will induce the electric pulse. Okay. Inside the material, when I apply magnetic field, what will happen? Same thing will occur. Magnetic domain will move, and this motion of magnetic field or motion of magnetic domain to align themselves in the direction of external magnetic field, this motion will generate a electric pulse. Okay, this pulse is very important to assess the health of manufactured component or assess the health of material. I repeat, doctors uses the pulse from the hand. Doctor uses the pulse from hand like this, and then they use this pulse to identify the health of the patient. Similarly, we can capture this pulse by a sensor. So I repeat, if we are having a moving magnet and ammeter, the domain will generate a signal or pulse. This electric pulse that is coming out from the material, I repeat, when this pulse is coming out from the material due to motion of magnetic domain, this pulse can be very easily sensed by a simple sensor in form of a signal, and then this signal can be used to assess the quality, how this signal can assess microstructure, how this signal can assess micro hardness, or most importantly, how this signal can assess residual stress, that we will see by using the instrument again or by using the coming slide. So in material, the domain wall or the motion of magnetic field occurs in jumps. So in this simulation, you can see that motion of magnetic field is occurring in form of jumps. So this motion of magnetic domain is not smooth. Why this is not smooth? Because material is having imperfections or defect, like it is having void, it is having porosity, it is having carbide inclusion, it is having secondary particle. So when domain wall will move over this, it will jump like this, it will jump like this, like the jump of your motorcycle bike when it is moving over the speed breaker or any pit over the road. So your motorcycle or cycle also get jumps. Similarly, the magnetic domain wall will also get jerk or it will get jumps. So by collecting all these jumps, we can capture a signal like this. So each spike is indicating burst of Barkhausen noise signal. So this is the signal that we will obtain by that sensor. This signal is very important to assess the health or to characterize the material. How we can assess? We can use the mathematics, we can use the mathematical curve, because mathematical curves are having some parameters. So we are going to use a mathematical curve. You can see that a red color envelope or red color curve is there. That red color curve has enveloped the Barkhausen noise signal or this raw signal. This curve is utilized to assess or to characterize the material. The name of this signal is Barkhausen noise signal, and this comes because of change in global magnetization of material when we apply external magnetic field. Why this Barkhausen name is there? Because this signal was detected first by Professor H.G. Barkhausen. He was German professor, and initially in his laboratory he detected this signal by a rushing sound through a very small loudspeaker. That is why the name is Barkhausen noise signal. Loudspeaker indicate noise, so the signal name is Barkhausen noise signal. The signal is having a envelope or curve. If we plot this curve, that is red color curve, over a graph, and the graph is having x-axis and y-axis, this x-axis is indicating the applied magnetic field and y-axis is indicating Barkhausen noise signal magnitude. Then this is the location of curve. So we can see that x-axis is the input, it is the applied magnetic field, and y-axis it is the output in terms of Barkhausen noise signal amplitude. This curve is having various parameters like root mean square value or RMS value. This RMS value is directly related with residual stress. The amplitude or the peak value of this curve is related with micro hardness or grain size of the workpiece material or the manufactured component. The peak position means position of peak on x-axis indicate the microstructure or phase of manufactured component. So how this signal will utilize? Let us see. If two component I have to compare, okay, and one component is having higher micro hardness. I repeat, one component is having higher micro hardness, second component is having lower micro hardness. So micro hardness is nothing but it is the distribution of grain size. If grain size are very small, if grain size is very small, it means grain boundaries are more. Grain boundaries act as a hurdle to motion of magnetic domain. I repeat, grain boundary act as a motion hurdle for motion of domain wall. So if the material is having fine grain size or large grain boundary, more hurdle will occur in the domain wall motion and the amplitude of the Barkhausen noise signal will decrease like this. So by comparing the peak or amplitude, we can easily assess the micro hardness or grain size of the component. Now the second question, how we can assess the microstructure. Let us take example of two microstructure. One is perlite, another is ferrite, or you can say ferrite and martensite. Very common example of microstructure or phase I am considering. Ferrite is considered very soft for magnetization. I repeat, ferrite microstructure is considered very soft or very easy to magnetize. So in this case, the input or applied magnetic field strength is very less. Suppose this is the magnitude of applied magnetic field or input for magnetization or for magnetization of a structure that is having ferrite. If the second component is having more martensite, then martensite is considered hard to magnetize. If it is considered hard to magnetize, प्रखर मैं एक ऑनलाइन मीटिंग में हूँ, मैं यहाँ से फ्री होते ही बात करता हूँ, ठीक है, ठीक ठीक मैं बात. So if the component is having martensite, then what will happen? It is hard to magnetize. So the amount of magnetic field that will be used or the amount of input that will be used, it will be quite more. So this red color is indicating the curve that we will obtain from a component or manufactured product that is having more amount of martensite, and red color is indicating the component who is having more amount of ferrite. So by comparing this peak position, I repeat, comparing this peak position on x-axis, we can easily identify the microstructure or phase of component. So we have seen that by using this technique, we can get the Barkhausen noise signal within 1 minute, and in this 1 minute, we are able to identify the grain size, micro hardness, microstructure, as well as different phases. That is why this smart technique nowadays is getting popularity among scientific people to use this for characterization of material. The big question is still unanswered. The big question is how we can use this technique for assessment of residual stress, because nowadays we are using X-ray diffraction technique. We came to know about the limitation or disadvantages of X-ray diffraction technique. So it is very essential to know the principle of this technique, Barkhausen noise technique, for assessment of residual stress. Hysteresis loop is always associated with magnetism. Whenever you are going to study magnetic field, you have seen in 10th class physics or 11th class physics or 12th class physics, always we have to study the hysteresis loop whenever we are going to study the magnetism. So here also we will see briefly the generation of hysteresis loop. So hysteresis loop is associated with application of magnetic field. This hysteresis loop we have also generated in our display when we were using the when we were using the Barkhausen noise technique. This hysteresis loop is generally drawn on x-axis and y-axis. X-axis is indicating the B value, that is the magnetization inside the material, and H is indicating the applied magnetic field strength. I repeat, on y-axis you are having magnetization of the material, and on x-axis we are having H, that is applied magnetic field. Hysteresis loop is very much related with the material property. You can see the change in shape and size of hysteresis loop when we are having two different material, soft magnetic material and hard magnetic material. By changing the shape, we can identify the material property or quality of the workpiece material. You can see when the soft magnetic material hysteresis loop is intersecting the x-axis and y-axis, it is a different point. And when the hard magnetic material you are using and the hysteresis loop you are obtaining from the hard magnetic material, it is having very wide shape. Soft magnetic material, very narrow shape of hysteresis loop. This is very important because we can correlate with the we can correlate the mechanical property or material property by magnetic property. So this is very important figure that indicate that we are having direct correlation between the magnetic property and material properties. So we came to know that mechanical property like yield strength, tensile strength, hardness, microstructure phase, and residual stress, they are well connected with magnetic property. Magnetic property we can obtain by hysteresis loop as well as Barkhausen noise technique. The hysteresis loop is generated when we apply alternative current. So you can see the application of alternative current, and this alternative current has generated the hysteresis loop. This hysteresis loop, when plotted over the x-axis and y-axis, it is having intersection point with x-axis and y-axis. These intersection point of hysteresis loop with x-axis and y-axis are indicating very important property, magnetic property. Like you can see that whenever the hysteresis loop is crossing the x-axis, point D and point G, just look into point D and point G, it is coercivity. And when this is a magnetic property, and when we see the intersection of hysteresis loop with y-axis, point C and point F, it is remanence or retentivity. These magnetic property like coercivity, remanence are magnetic property, and they are very much related with material property because of direct correlation. One important property is permeability. What is permeability? If I draw a tangent, see the red color tangent, this red color tangent, if I draw at the knee of hysteresis loop, then the slope of this tangent will indicate the permeability, and this is directly correlated with the residual stress. So now we are having this information that magnetic property like coercivity, remanence, permeability, hysteresis loop, they are related with mechanical property like grain size, hardness, residual stress, and microstructure. And experimentally and analytically, it has been well proven by scientific community. So we can use these hysteresis loop parameter for assessment of material health because of direct connection between the magnetic property and mechanical property. So this is animation of generation of Barkhausen noise signal and hysteresis loop. In case of generation of Barkhausen noise signal, we are using magnetic field. This magnetic field is having two very important parameters. First one, strength of applied magnetic field. I repeat, strength of applied magnetic field. And second very important parameter is frequency of applied magnetic field. I repeat, F, small f, that you can see it is 1 hertz here. Frequency of applied magnetic field is also very important. When we increase the frequency of applied magnetic field, the magnetic field that will penetrate inside the material, it will decrease. Okay, please be careful. When we increase the frequency of applied magnetic field, the penetration or the depth of penetration of a magnetic field inside this material, it will decrease. And when we reduce this applied, when we reduce this magnetizing frequency, the depth of penetration of magnetic field inside the material, it will increase. So in magnetizing frequency is inversely proportional to penetration depth of magnetic field. This important is very important because in case of X-ray diffraction technique, we have seen that we are able to see the quality of 10 micron depth of the workpiece thickness. Here, in case of Barkhausen noise signal, we can change the magnetizing frequency as per our requirement, as per our desire. So we can change the depth of penetration as per our wish. Now you can also see that in this simulation, if I change the frequency, it will change the depth. So this is the different magnetization frequency. This is 50. You can see the depth. This is frequency of 1 hertz. Now this is applied magnetic field at 50 megahertz. So you can see the change in magnetic field and hysteresis loop generation. And this is at 20 megahertz. You can see the generation of Barkhausen noise signal and hysteresis loop formation at 20 megahertz. So that is the most important advantage. We can play with the penetration depth. This was not possible in case of neutron diffraction technique. This was also not possible in case of X-ray diffraction technique. But in this magnetization technique or Barkhausen noise technique, it is very easily possible. Principle of magnetization. What is this principle of magnetization? In previous slide, we have seen that when we apply magnetic field over the component, when I apply magnetic field over the component, magnetic domain wall will move inside the material. This magnetization movement or this motion of magnetic domain will occur so that they will align themselves in the direction of magnetic field. Okay, this motion is completed in 3 steps. First one, A to C. So in case of hysteresis loop, you are able to see point A and point C. A to C is indicating elongation portion of magnetic domain. Point C to D is indicating domain wall movement. And point D to E is indicating the rotation of domain wall. After point E, domain wall will align themselves in the direction of magnetic field that you can see in the figure. The rectangular block at E point is indicating that magnetic domain have aligned themselves in the direction of magnetic field. This is known as saturation condition or saturation state. After this, if I increase the magnetic field, nothing going to happen because that is the saturation state of material, like saturation state of human being. Suppose my capacity is to eat 5 aloo paratha in lunch. I can take 5 aloo paratha in lunch. After this, if you offer me 6 aloo paratha or 7th aloo paratha, I will simply not take it. In the same fashion, material has acquired its saturation state. After this, if we are increasing the magnetic field, nothing is going to happen. Okay. So what is this elongation, magnetic domain wall movement or rotation that we can see here in this slide clearly. So this slide is indicating point A, point B, point C and point D. From point A to B, the path is indicating elongation. From point B to C, the path is indicating domain wall movement. From point C to D, The path is indicating rotation. So hysteresis loop is always associated with generation of Barkhausen noise signal. The hysteresis loop is combination of magnetizing curve and demagnetizing curve. The combination of magnetizing curve and demagnetizing curve generates the complete hysteresis loop, and we are having two Barkhausen noise signal. I repeat, we are having two Barkhausen noise signal from each magnetizing yoke. Just a minute. To be elongation, and it is contributing very less generation of Barkhausen noise signal. Path B to C, from point B to point C, the path is domain wall movement, and this is significantly contributing in generation of Barkhausen noise signal that you can see. And from point C to point D, it is the rotation, and this C to D rotation is contributing again very less in generation of Barkhausen noise signal. So now what is the meaning of elongation, domain wall movement, rotation? We will see. Hello?
Sir, your PPT is not visible. Please share.
Okay, again I will share.
Yes, sir.
Is it visible now?
Yes, sir.
Okay. So we came to know about the motion of magnetic domain wall, elongation, magnetic domain wall movement, and rotation. This we can easily understood by considering this example of permanent magnet. Permanent magnet is having north pole, that is N, and south pole, that is S. I am considering a alpine in shape of a arrow. So you can consider this arrow as a alpine. This alpine is having a tail and a head. Okay. In case of alpine, it is characterized by tail and head. So when I apply magnetic field by this permanent magnet, what will happen? This is the domain or external boundary of magnetic domain or magnetic field. When this alpine will receive energy from magnetizing field, what will happen? It will elongate itself. I repeat, the energy has been received by alpine and it will elongate. This elongation is motion from A to B. Okay, so this elongation is indicating motion from point A to B. Now the energy is continuously going into the alpine, so it will again move. This is the second stage, motion of magnetic domain wall, point B to C. So you can see that alpine has moved or it has attracted toward the permanent magnet by completing domain wall movement from point B to C. remaining third stage is very important, because you have also seen the magnet, if it is attracting a alpine, the alpine cannot stable itself in this alignment. It will rotate itself, it will stick to the permanent magnet that is completed by this rotation. So the third stage is C2D, that is rotation, and this is completed like this. Okay, so now the alpine is in alignment with the direction of magnetic field, and it has acquired its saturation state. So this motion of magnetic domain wall will generate the Barkhausen noise signal, and it is associated with hysteresis loop like this. Now, very important conclusion we are going to derive: principle of magnetization. We have seen how this principle of magnetization is used in case of assessment of residual stress, that we are going to see here. Principle of magnetization is indicating when we apply magnetic field, it supply magnetization energy to the domain wall, and these magnetic domain wall will receive this magnetization energy for completing the motion by three stages. First one is the elongation, A to B. Second one is the domain wall movement, B to C. And third one is the rotation, C to D. So this is the principle of magnetization that we have seen in previous slide. How this principle is used in application for assessment of residual stress. Again, the same block I am using, but it has been little bit modified. When we apply magnetic field over two components, suppose I am having two components, this is first component and this is second component. First component is a component that is not having grinding operation, and this second component is having a grinding operation. Now you will come to know that why I have selected grinding for explanation purpose. This second component is having a grinding operation. It means it is having tensile residual stress, and this component is not having grinding operation, so it is not having tensile residual stress. So when I apply magnetic field, it will supply magnetization energy for magnetic domain wall movement. And in case of second component, that is ground component, what will happen? Tensile residual stress has elongated the cracks, the porosity, the void, the grain boundary. They have also elongated the domain wall. I repeat, induction of tensile residual stress, they will elongate the porosity, void, microstructure, grain boundary, and in the similar way they have also elongated the magnetic domain wall. So domain walls are already in elongated state in ground sample, hence the magnetization energy is available more in quantity for magnetic domain wall movement. So the level or amplitude of Barkhausen noise signal will improve, or it will range like this. So in this fashion, we can say when the component is having, manufactured component is having tensile residual stress, it is having low Barkhausen noise, it is having large or bigger Barkhausen noise signal in comparison to the component which is having compressive residual stress. So this technique, this is the Barkhausen noise analyzer. This is available in IIT Kharagpur. You can see the principle of this Barkhausen noise analyzer. It is having very common component like magnetizing yoke. It is having amplifier. It is having band pass filter. It is having low pass filter. It is having sensor or pickup coil for picking up the signal. It is also having a display unit. These are the screenshot of Barkhausen noise analyzer that we will see when we will demonstrate this technique again. So hysteresis loop is there, Barkhausen noise signal is there, their parameters are there like peak value, RMS value, FWHM, peak position, coercivity, remanence, permeability. So these parameters we will see again during the demonstration of this technique over a component. So this technique is used in experimental purpose. You can see a graph that is between depth of cut or in feed and residual stress. What is the meaning of this graph? In feed or down feed or depth of cut means the grinding operation, penetration of grinding wheel into the workpiece, that is the depth of cut. Okay, so depth of cut of grinding wheel into the workpiece on x-axis, and on y-axis it is the amount of residual stress measured by X-ray diffraction technique. So this is the rising curve or increasing curve. It is indicating when we increase the depth of cut, we are getting more or more amount of residual stress. This is the Barkhausen noise curve with same grinding parameter like in feet, and you can see RMS value, peak value, and area under amplitude spectrum. But here the graph is increasing to some point and then it is decreasing. Why this deviation in curve? Because dislocation density has increased in larger quantity. That is why we have obtained a deviation in curve. Otherwise, we are getting a very good correlation between the residual stress and Barkhausen noise parameter. So these are experimental result, actual result, which are indicating the application of Barkhausen noise technique, and experimentally it has been proved. Just look at these graphs. It is indicating the correlation, a great correlation between X-ray diffraction technique and Barkhausen noise parameter data. These are indicating very good correlation between the Barkhausen noise parameter like RMS value, peak value, area under the curve, and residual stress obtained from X-ray diffraction technique. So this is the recent advancement in surface characterization. In case of advanced manufacturing industries now they are adopting this Barkhausen noise analyzer for smart characterization of material. We can see Bark Mumbai is having this technique. IG Car, that is Indira Gandhi Center of Atomic Research, Kalpakkam, it is also having this technique. IIT Kharagpur is also having this technique. Bharat Forge is also having this technique. So various manufacturing industries, leading manufacturing industries, Tata Steel is also having this technique. So they are adopting this technique for a smart characterization of material. Now again, we will look into the application of this technique so that you will better know the application of this technique. I am going to stop this. So again, we are repeating the experiment or using this technique. I hope so. This analyzer is visible to you.